We're looking here, I'm guessing, on page 23 of your unit handout. And we're going to be looking at, over the coming, I would say, at least 4 days of classes, maybe more, depending on lab work and quizzes and assignments, we're going to be applying Newton's second law of motion. By the way, just a reminder here, Newton's second law of motion is that the net force acting on a mass will always be equal to its mass times its acceleration. And as we've talked about last week a couple times, Ephraim asked about direction and negatives and what you put in formulas. Most of the time we're going to be using this form of Newton's second law and building in the direction by subtracting forces instead of having negative forces. Okay, and we'll get to that today. So we're solving various problems involving applications of Newton's second law. And we're going to be looking today at vertical motion examples. So everything we deal with today is objects accelerating up or down or moving up or down. And I'm going to start with example 2. And I've never started with example 2 before, but I have an idea in my head. I want you, and I don't want you to write anything down, I want you to take a look at this question. Read this question carefully. And the question says, what is the applied force required to accelerate a 250-gram rocket, which, by the way, is 0.25 kilograms, required to accelerate that rocket upward at 32.4 meters per second squared? And I want you to calculate what you believe the answer to this question is. I'd be willing to bet I don't think anybody got the right answer. Or, if somebody got the right answer, I'm going to be very impressed. Very impressed. And the reason I'm doing it this way is I want to illustrate to you that things are not as simple as you think they are. You get this on an exam and you get 8.1 newtons, which is what I'm guessing everybody got. Most of you, maybe you don't want to admit it, you went MA, right? That is not the answer to this question. Because you're not asked to find the net force, you're asked to find the applied force. And for everything we do, and I know that sometimes it's like I stress things because it's like the most important thing in the world. This is important in physics. Any application of Newton's second law of motion now has to be accompanied by first drawing a free body diagram. Drawing a free body diagram. So, we need a free body diagram. Now, rather than embarrass myself and try to draw a rocket, I'm just going to draw an object, okay? So we have an object. Doesn't matter what it looks like. And we have to draw a free body diagram. If you don't draw a free body diagram, and the problems are going to get more complex as the days go on, you will not get the right answer. Well, there is definitely a force of gravity. And by the way, if you got the 8.1 newtons, it's because you didn't take into account the force of gravity. And there is an applied force upward. Now, just a second here. Look at my free body diagram here. Don't draw what I'm about to draw, but can this possibly be a reasonable drawing for the free body diagram? No, the applied force upwards needs to be greater. Without really knowing the answer to the question, we can't really draw it to scale, but I will tell you that it's probably going to be significantly bigger. Well, I shouldn't say that. Let's just draw it bigger. Gabrielle, why does this applied force up? Give me a second, sorry. I should have drawn this first. Why does the applied force up need to be larger in magnitude than the force of gravity down? Right, it's moving upwards against gravity, and we could even add a better word in there, or another word, an adjective, or a verb. It's accelerating up. So the net force must be up. So this is your first step in solving any of the problems that fall under this heading, application of Newton's second law. Today, tomorrow, Wednesday, Thursday, Friday, whenever. Your second step is to write Newton's second law of motion. And I'm going to go with what I just discussed near the beginning of this lesson, with just magnitudes. The magnitude of the net force must be equal to the mass times the acceleration. And then your third step is to write what the net force is by looking at your free body diagram. Looking at the free body diagram, the net force will be the magnitude, well, the magnitude of the net force will be the magnitude of the applied force minus the magnitude of the force of gravity. And this is equal to m times the magnitude of the acceleration. So not to belabor a point, Ephraim, but I keep coming back to this because I think it's important, and you had asked about it. Rather than me saying up is positive and down is negative, all I'm doing is I'm looking at the diagram and saying the magnitude of the net force is the bigger force minus the opposing smaller force. If it were the other way around, if there was an applied force up that was smaller, then I would have written the magnitude of the force of gravity minus the magnitude of the applied force. It's always going to be bigger minus smaller. We can drop all of this pretense with the absolute value signs and all of this and just write the applied force minus mg, because that's how you calculate the force of gravity, is equal to the mass times the magnitude of the acceleration. There were one or two of you that on the little mini lab thing that I took in and marked, there were one or two of you that wrote, and please don't write this down, this for a formula for weight. Weight, which is the force of gravity, is not ma, it's mg, right? So here's a perfect example why we can't just confuse those, because we have a g in this formula that we've created and we have an a. Let's put in the numbers. Rather than rearrange it, well, it doesn't matter. We could rearrange it, but I'm not going to. The applied force equals the mass, which is 0.25 kilograms, times 9.81. And I would prefer if you put units of newtons per kilogram whenever you write G. Equals the mass, which is 0.25 kilograms, times the acceleration, which is 32.4 meters per second squared. Now, both of these things will give us newtons. And I'm not after just an answer here. I'm after me explaining what's going on. So I would like you to calculate each of these terms separately. The applied force will be equal to, do you have a question, Ephraim?
Yes. Should I avoid getting rid of the masses?
Yes, it's a good question. You can't get rid of the mass here. There's going to come a time, so let's look back up here to answer Ephraim's question. Ephraim is saying, can I get rid of the masses? And by get rid of, I hope you mean divide both sides by m to cancel them. Well, the answer is no, you can't. If you do, and not everybody is going to benefit from what I'm going to write, but some will, and if some benefit, that's good. If I divide everything by the mass, I will get this. I can't selectively just divide two of those terms by the mass. I have to divide every term by the mass. And I think that this equation that I've written in red is more confusing now than anything else. Because you want to get the applied force, so you're going to solve for the applied force over m, and then you're going to have to multiply by m anyway. You can, but you don't get rid of it. It's still there somewhere. We are definitely going to see situations here, Ephraim and everybody, where we will have an equation where mass is in every term, and then you can get rid of them. So we're calculating these. Is this 2.4505? Okay. Whoops. And I've made a mistake here in what I've written. This is minus, right? Okay. So I get the applied force minus 2.4505 newtons is equal to whatever this is. And by the way, this thing, this 0.25 times 32.4, that's the net force.
I think it's 2.45.
2.2505?
Not a 0 or 2.
Oh, 2.4525.
4525.
Okay, 4525 newtons. Sorry about that. And this is equal to, this is equal to that 8.1 that you thought was the answer. So now, what is this saying? It's saying that the applied force is going to be equal to the net force plus that weight of the rocket. So for those of you that, when I said go ahead and calculate, you got 8.1, you found the applied force in a weightless environment if there was no gravity. But think of it this way. You have to apply 2.4525 newtons just to overcome gravity, and then you have to apply that 8.1 to get the acceleration to be what it is. So the answer is actually 10.55 newtons. And I'm not worried about rounding here. I'm just writing an answer, okay? So what turns out to initially appear to be a very simple question. Oh, you're writing an exam. Mr. Way felt sorry for us. He made the first question of the exam so simple, I just go MA. No, I didn't. I didn't make it simple. I don't ask those simple questions because that's science 10, right? So the answer to the question is you need an applied force upward of 10.55. Now I'm curious, gentlemen, where the 17 point something came from.
FG is mg. I kind of forgot that. And I just put 9.81.
Okay. So you understand why this is the way to go. Okay. So let's take a look now at example 1. Because example 1 is maybe a little bit different. It appears different anyway. A person and an elevator have a combined mass of 600 kilograms. The elevator cable exerts a force of 6,500 newtons upwards on the elevator. What is the acceleration of the person? Which means, what's the acceleration of the person in the elevator? Well, the first thing that you need to do is draw a free body diagram. But we need to explore something here. Is the person accelerating up? It doesn't say. It doesn't say anywhere in this question whether the elevator is accelerating up or accelerating down. The only way to determine what the acceleration direction is to compare the forces. So we know that there is a force upward. It's the tension in the cable, but it's being applied to the elevator and the person of 6,500 newtons. This is what we call the applied force. But we also know there's a force of gravity. Now, I don't feel comfortable in just assuming that the elevator accelerates up. When you're in an elevator and it first starts moving up, you feel a little bit heavier, don't you? That's because the elevator is accelerating up. But when you leave the top floor and you start moving down, there's that feeling of weightlessness briefly, or you feel lighter. That's because the acceleration is downward. We don't know. So how can we find out? Let's calculate the force of gravity. Right, just off on the side someplace. Force of gravity has a magnitude of the mass, which is 600 kilograms, multiplied by the gravitational field strength. And I really, again, I would be really happy if nobody ever in the universe referred to this thing as acceleration due to gravity in this context. It's gravitational field strength. Because it's not an acceleration. Well, it's your acceleration if the cable broke. Okay? So, well, I can see it's going to be less than that. $600 multiplied by 9.81, 5886. Well, that's less than 6,500. You don't need to get out a ruler and measure these lines to scale. You know, just make sure that it's less. So this is the force due to gravity. It happens to be equal to 5886. And this time we want the acceleration. In question 2, we wanted to find the applied force. But fundamentally speaking, if you take a look at this free body diagram of what's going on to the elevator and the person, it's no different than this, isn't it? It's the same thing. Yes? Okay. So what we're going to do is we're going to say that the net force has a magnitude that's equal to the applied force up minus the force of gravity down. So that means MA that means that MA is that applied force upward of 6,500 newtons minus mg, which is 5886 newtons. And the mass was, I believe, 600 kilograms. So you have to subtract those two forces to get the net force. Well, you have to subtract the two magnitudes to get the net force, and then divide by the mass, and that will give you the acceleration. But 1.02 meters per second squared, and this will be up. So I'm converting it back to a vector here, and I'm saying what's the direction. And going back to that whole negative business, you can't just do this problem by putting in negatives for g. I mean, there's a way to do it, but it gets complicated. The only way you know it's up is you've calculated the forces in this case and compared them. The force upwards is greater than the force downward. Capiche? Okay. Let's take a look at number 3. Skydiver is jumping out of an airplane during the first few seconds of one jump. The parachute is unopened, and during that time, there is a force of friction of 250 newtons acting between the skydiver and the air. It's like putting your hand out of a moving car's window. You feel the force of friction pushing you backwards. So what does the free body diagram look like? I just lack imagination today. If I had more energy, then I would attempt to draw a skydiver so that you could laugh at me, but I'm not going to. There will be a force of gravity down, and there is a force of friction up. I don't know which one is bigger. Based on the question, though, actually that's not true. I do know which one's bigger. The force downward is bigger because when you jump out of a plane, you end up moving downward, right? What I meant to say was I don't know how much bigger it is, but this is only 250 newtons. And in my mind, what I'm doing is, well, we're asked to find the mass. The typical mass of a person might be 50 to 75 kilograms. Maybe more, it depends on the person, right? But if it's 50 kilograms, 50 times 9.81 to get a weight is almost 500. It's well beyond the 250. So we're asked for the mass here. I'm going to look at my diagram now. I guess I should label this. This is the force of friction. And this is the force of gravity, whose value we don't know. We don't know the force of gravity because we don't know their mass. So the net force in this case will be the force of gravity minus the force of friction. And every time I say that, I feel as though I need to correct myself. The magnitude of the force of gravity minus the magnitude of the force of friction. This is MA. This is mg, and this is the force of friction, which we know the value of. So let's put the numbers in. Let's put the numbers in. The mass we don't know. The acceleration is 5.96. The mass we don't know. The value of g is 9.81. No, and then minus the 250. So there's no negative 5.96 because they're accelerating down. The net force is down, so we set it up this way. Before we proceed, although the meters per second squared describes an acceleration and the newtons per kilogram describes a gravitational field, they are the same units, aren't they? Okay, let's keep that in mind. So we want to solve this for m. If you were ever solving a math equation, let me write this down. 5.96 m equals 9.81 m minus 250. This is a basic grade 9 math equation. You want to collect all of your terms with your unknown to one side, and I'm going to choose to take this 9.81 m is the mass, and subtract the 5.96 m, and I'm going to move the 250 to the other side. So I have rewritten the equation. For those of you that might struggle with the math of it, I've rewritten the equation so the units are not in it, to help you better understand how we're going to solve this. When you have two terms being subtracted and they're both similar terms, they're both m's in this case, then you subtract the coefficients. Just looking up here for a minute, if this is 10, just think about it. If this is 10 and this is 6, 10 kittens minus 6 kittens is 4 kittens, right? The analogy kind of breaks down because I don't want to start talking about what 9.81 kittens is like. It's part of a kitten. 9.81 m minus 5.96 m is the difference between those two numbers, m. And my brain is not up to carrying and subtraction here. So 9.81 minus 5.96, 3.85 m. So now we can divide the 250 by the 3.85 and get the mass, and this mass will be in kilograms. About 65 kilograms. And that question is certainly more challenging because even when you set up the physics properly, which in and of itself is a little bit of a challenge sometimes, you're left with a variable that you have to find in two places in the equation. Let's take a look at the next question. And if I've planned things right, this should be the final example. It is. So we have a 3,200 kilogram elevator. What is the tension in the cable? So before we start, the tension in the cable will be the applied force upward. And with a little bit of thought, I hope you understand that the tension in the cable must always be upwards, whether you're accelerating up or accelerating down. If the tension in the cable is downward, it would be a wild ride, right? You'd be accelerating downward faster than 9.81 meters per second squared, which means you'd be hanging out on the ceiling of the elevator. Okay? So the applied force must be upward. What do we do? And I want to set this up for each of A, B, and C before we calculate any answers. What do we do when there's an upward acceleration? Well, in general, if there's an upward acceleration, the applied force upward is more than the force of gravity in magnitude. That's what's going on. And if that's the case, everybody, then you would write F net equals F applied minus Fg. I mean, look at the diagram. You take the applied force, magnitude of the applied force, and you subtract the magnitude of the force of gravity because they're in opposite directions and the applied force is greater. What do we do, or what does it look like in B if the elevator is accelerating down? Well, if the elevator is accelerating down, you have that force of gravity, you have a smaller applied force upwards. And that means the net force, which is the sum, I don't think I've actually said this today because I think it's obvious, so maybe I shouldn't think that for everybody. The net force is the sum of all the forces. That's what net means. So you have to add these forces together by looking at your diagram, and it is going to be the force of gravity, the magnitude of the force of gravity, minus the magnitude of the applied force. And if you take a look at the subtle difference between these two, I'll just freeze this one up on the right screen. So look at the formula for F net here. When the elevator is accelerating up, it's the applied minus the force of gravity. When the elevator is accelerating down, the net force has a magnitude of the force of gravity minus the applied force. How many of you, and I ask this because I used to do it all the time, I would solve math problems, I'm thinking maybe back in junior high, and sometimes I would get a negative answer when I subtracted, and I knew it shouldn't be negative, so I just forgot about the negative. How many of you have encountered that? It won't work here. This, because there's a third term, it really messes things up. You'd be surprised. So you have to be very careful about that. All right, let's take a look at C, and then we'll go back and we'll do the calculations. The elevator is moving up at a constant speed. So what does the free body diagram look like? Well, we need the object, and we know there's a force of gravity. And we know there's an applied force upwards because if there weren't, you'd be just in free fall. The question is, how big should I draw the applied force upward? Has to be equal. Why is that, Sam? It's not accelerating. Some people will say it has to be a little bit more than the force of gravity because you're moving up. No. There was a force that was more than the force of gravity upwards to get you to 4 meters per second, but at that point in time, the forces are balanced. I used to have really hearty discussions with my dad to try to convince him that when you're driving down the road at 100 kilometers per hour, the net force on your vehicle is 0. Because he would say, well, you need more force forward to keep moving forward. And no. If the forces are balanced, the acceleration is 0, the net force is 0, period. So in this particular case, we draw the applied force, and there's two ways we can build the equation. One, we could say this, but now, which order do you subtract those in? Does it matter? No. I think people who do this are maybe asking for trouble. Applied minus force of friction. And then they would say MA is applied minus force of friction. And then they would say this is 0 because the acceleration is 0. Right? And let's make a note here. This is not an acceleration, this is a speed, equals applied minus force of friction, which means the force, I'm not sure why I went to friction when it should be gravity. Which means the force of gravity is the same as the applied force, and I think it's just more reasonable to start with that. You don't have to really use the F net idea. So to solve these problems is now child's play. This is MA equals the applied force minus mg. What was the mass? 3,200 kilograms. So this will be 3,200 kilograms. Just for kicks, let's leave the units out for this one. Whoops. Just take a minute, don't calculate anything yet. Just let that sink into your brain. How many of you would feel more than comfortable just bypassing that middle line? That's fine. So the applied force will be 3,200 times 2.5 plus 3,200 times 9.81. So I'm getting about 39,000 newtons. Let's call it 3.9 times 10 to the 4 newtons. Why would this even be of interest to us? Well, if you're in engineering and you're designing a new lift system for something, then you would need to know what kind of cable to create or use in your lift system, and it had to withstand at least that tension. If we have this question, then it's going to be MA times 3.5. Again, the direction is built into how we set up the equation. We're not going to put negative because it's down, bless you. Equals 3,200 times 9.81 minus the applied force. I don't like negative things that I'm trying to find, so I move that to the other side where it becomes the positive of the applied force, and it will be 3,200 times 9.81 minus 3,200 times 3.5. Do you get the same answer? Good. 2.0 times 10 to the 4. And then for the third one, all we have to do is find the force of gravity, because that has to be the applied force. Whether the elevator in question C is moving up or down at a constant speed or is being held with no speed, the weight will be the applied force. So it's simply going to be 3,200 times 9.81. This will be our answer. And I'm getting 3.1 times 10 to the 4. You know, well, we'll stop there. Any questions? There's going to be a tendency here, and I have some experience with figuring out how some students learn, and some students want to memorize things. That maybe, and this is okay, maybe when the elevator or the person or the rocket is accelerating up, the applied force is the net force plus the force of gravity. And when it's accelerating down, it will be the force of gravity minus the applied force equals the net force. But what I want to impress on you is it's not always going to be that simple. Keep in mind, this whole heading is called Applications of Newton's Second Law. And this is just with vertical motion. What if it's on an inclined plane? What if it's on an inclined plane and the object on the plane is attached to a pulley at the top and there's a force of gravity down? You're not going to be able to memorize all of the different formulas that we create. So what you do is you always draw a free body diagram, set up your formula based on that. If you're going to try to rely on memory, your memory is going to falter from time to time. It's just not going to be reliable for most people. So, again, we don't have to worry about the vectors. There's Newton's second law as it appears on your formula sheet. Always draw a free body diagram showing all forces. If the problem is so simple that there's one force, then go ahead and use F equals ma. But otherwise, draw a free body diagram, use the free body diagram to find an expression for the net force, and then set that expression equal to ma and answer the question. That's what you do for all of these.